We have matched 10 workloads to their best structure. Now let's gather all the costs into one place you can look up later. This table is the compact map from what you need to what it costs. Each row names an axis, its best fit family, and the typical price. Let's read them one at a time. When you need to jump straight to position I, an array or dynamic array does it in big O of 1. When you look things up by a key, a hash table finds them in big O of 1 on average. When you need the items in sorted order, a balanced binary search tree keeps them ordered and searches in big O of log n. When you always want the largest or smallest item, a heap peeks it in big O of 1 and inserts or extracts in big O of log n. When you match by prefix, a trie walks the typed letters in big O of L, where L is the length of the prefix. When you ask whether two things are connected, disjoint set union answers in near big O of alpha of n, effectively constant. And when you sum over a range while values keep changing, a Fenwick tree or segment tree does both the update and the query in big O of log n. Now the detailed per family tables. First the sequence family, a fixed array, a dynamic array, and a linked list side by side. Reading position I is big, O of 1 in both array kinds because they know where each slot sits. A linked list must walk from the head, so it is big O of n. Searching an unsorted sequence is big O of n everywhere. You may have to check every element. Adding at the end is cheap for all three. Big O of 1 if the fixed array has room, big O of 1 amortized for a dynamic array, and big O of 1 for a list with a tail pointer. Adding at the front is where they split. Both arrays shift everything over. Big O of n, a linked list just relinks the head, big O of 1. Deleting at a known position is the same story. The arrays shift, big O of n. A linked list unlinks the node in big O of 1 once you are already there. The tree family part 1, search trees. A plain binary search tree next to a balanced one. A plain binary search tree searches in big O of h, the height. If it grows skewed like a straight list, that height becomes big. O of n, a balanced tree guarantees big O of log n. Insert follows the same height. A balanced tree stays at big O of log n by doing small rotations to fix its shape after each insert. Delete is the same picture. Big O of h for a plain tree, and big O of log n guaranteed for a balanced one. Walking all the items in sorted order is big O of n for both. You still have to visit every node once. The tree family part 2, heap and trie. Both are tree-shaped, but they answer very different questions. Inserting into a heap is big. O of log n inserting a word into a trie is big O of L, the length of that word. A heap peaks its largest or smallest in big O of 1. A trie has no extreme to peak, so that entry does not apply. Removing the extreme from a heap is big O of log n again. A trie has no such operation. A heap cannot search for a word. A trie finds a word or a prefix in big O of L. Keep these two symbols straight. Small n is the number of elements. Capital L is the length of the key or word you search for. A trie's cost never depends on n at all. That is its main advantage over a hash table for prefix queries. The hash family has one structure, the hash table. We compare its two ways of handling collisions, chaining and open addressing. On average, both chaining and open addressing find a key in big O of 1. In the worst case, when many keys land in the same place, both slow down to big O of n. Inserting is big, O of 1 on average for both. Once in a while the table grows and rehashes every key. That single step is big O of n, but it is rare, so it averages out to cheap inserts. Neither one can walk the keys in sorted order. If you need order, a hash table is the wrong choice. Reach for a balanced tree instead. The graph family. The two ways to store a graph: an adjacency list and an adjacency matrix. An adjacency list stores only the real edges, so its space is big. O of v plus e, a matrix reserves a slot for every possible pair, which is big, O of v squared. Asking is U connected to v costs big O of the degree in a list, but only big O of 1 in a matrix. That is a single direct cell read. A breadth first or depth first traversal visits every vertex and edge. Big O of v plus e with a list, but big O of v squared with a matrix. Dijkstra with a heap runs in big O of v plus e times log v on a list, much better than the matrix's big O of v squared for sparse graphs. Last, the specialized structures. Each of these four solves one narrow problem better than any general-purpose structure could. Disjoint set union merges groups and checks membership with its union, and find operations, in near big O of alpha of n, effectively constant. A Fenwick tree updates one point and sums a range, both in big O of log n. A segment tree does the same update and range query in big O of log n, and it handles more kinds of range questions. A monotonic deck pushes and pops from both ends in amortized big O of 1, exactly what the sliding window maximum needs.